Happy Friday, CS109. How are you guys doing today? Awesome. I appreciate that. I also appreciate it because I know it's a Friday, and I know it's a Friday before the midterm. So, wow, do I appreciate you guys coming to class. Thank you so much. A couple quick things before we jump into things. Because it's a Friday, I'll start by telling a story, as always. And I think the last time I told you the story of how I met my wife. Is that right? But where did we end up? Did I get in the truck? Yeah. And did I make it all the way to Romania? Yes. Oh, okay. So then, I get to Romania, and there I run into my wife again. And she's well, she's not my wife at the time. I run. And I say, hi, I made it. And then I got this wonderful story to tell her about how I took all these trucks, and I think she was very impressed. And at this point, it just was a great reunion. We had about 4 or 5 days together. It just felt fantastic. But as life would have it, she continued to have these exciting plans. She was going to go working at a refugee camp in Hungary for a while, and we thought we were going to go different ways. And we went different ways again, but the most serendipitous thing happened. A few days later, I was in a train in Hungary in the middle of the night, and it's kind of cold, and just mind my own business. And I'm talking a little bit to the person in the car with me. And then Laura shows up. Apparently, she had gotten into the same train in the same random part of Hungary the same night, and had sat down in the car right next to me. And then she heard my voice. She's like, what? The person who came all the way by the trucks to come find me in Romania? How did you end up here? And so at this point, we're like, oh my gosh, the world has brought us together in so many different ways. We ran into each other on the island a bunch. We managed to make it to Romania together. Now we ran into each other on a train. And at that point, we decided, hey, what if we intentionally ran into each other? So even though she was going to a different destination than me, we decided, hey, let's go meet up. And then we met up and we started traveling together. And then our paths didn't really go that different ways until this day. So that's the second part of the story of how I met my wife. And I'd suppose, even though there's this really cute meet cute, certainly the more interesting part of the story is the one where we got to intentionally choose to spend time together. And I got to know this wonderful woman. And all those moments, those are the really special things. The meet cute is just a nice, but that's not important right now. What is important is, oh boy, do we have a cool lecture for you guys. I appreciate you guys coming to this lecture. So I want to give you something very useful, very cool. We're going to be learning general inference. In particular, you're going to be learning an algorithm called rejection sampling. You guys might know some of the other professors at Stanford, but I was talking to a professor, Noah Goodman, who's one of the more famous modern statisticians of our times, happens to also be at Stanford. And we were talking, and I said, I think this is something I really want to bring into our Intro to Probability class because I think it clarifies so much. And he says, yeah, if there is one thing that I thought all interest probability people should see earlier, it's this idea of rejection sampling. So you're going to see a beautiful idea with Noah Goodman's stamp of approval. In today's class, we're going to do two things. We're going to finish our conversation about correlations, and we're going to be learning about rejection sampling. And it really comes around this beautiful idea that you guys saw on Wednesday called Bayesian networks. And in case people lost the plot, I put the whole plot line up here on the board. So the whole plot line of what we're doing is we would like to be able to solve beautiful, interesting, real-world problems with the power of probability tools. But most real-world problems have a lot of random variables. That in itself shouldn't be too big a problem, except it leads to this interesting computational problem. One of the most straightforward ways to represent many random variables together is a thing called a joint table. And a joint table is exponentially large. So as you have bigger worlds that you want to represent, a joint table would need exponential numbers of probabilities. That's both a space issue, and you'll have to do exponential amount of work in order to estimate those. Big problems. How sad. We wanted to do this, but we can't. Enter this great idea of Bayes nets that we saw on Wednesday. And Bayes nets is a way to represent a probabilistic model for a real-world problem, but it has this beautiful property that it's going to be O of n in terms of n, the number of random variables. So Bayes nets allowed us to do probability for real-world problems. Now that leaves two to-dos for you guys. You would need to know how to create a Bayes net, and you'd need to do this task that we call inference. But inference is just a fancy word for saying, do conditional probability in the context of this big random variable. If you guys have plot line questions, please do ask me. Now, towards this idea of a Bayes net, the key concept was if you can have some expression of which random variables cause which other random variables, you can really compress how you represent the joint distribution. But that would require you to be able to create a Bayes net. And there was this side plot in Wednesday's class, and I'd like to pick up on it. Oh, and of course, there's lots of real-world problems that you could think about, but our running theme has been WebMD. So WebMD, you say a bunch of symptoms, and it can tell you for all the possible diseases, the probability of you having all those different diseases. The Bayesian network was defined in a few ways. One of the ways it's defined is first you take all your random variables and you make them nodes in a graph. And then we're going to draw lines in a directed way from nodes that we think are causally impacting other nodes. So we think flu causes you to have fever and flu causes you to be tired. Now there is a big asterisk here in the O of n, is that this O of n kind of assumes that you don't have too many arrows. So if you have a sparse number of arrows, then you get the nice compression. Once you draw arrows, you have to give the probability of every random variable given its causal parents. And if you do that, that's your compressed way of representing the entire joint distribution. So for every probability, give it the probability of the node given its parents. So for example, tired has two parents, flu and undergraduate. For every combination of values for its parents, you have to give the probability of tired. But if you do that for every random variable, you defined a joint in a very compressed way. Wonderful. There is a semantic way of thinking about these Bayes nets, why they're so amazing. And one way of thinking about it is that they're generative. They tell you the story of how the joint comes to be. And the story that's told here is first, people have these priors, whether or not they have the flu or whether or not they're undergrad, and then we generate whether they have fever from those. So it's like the world gets generated from top to bottom. And I really like this idea of thinking generatively and thinking about the process from which a joint is created. It's not just for WebMD. You know, there's lots of different situations where people might use these, like figuring out why you have communication loss or battery failure for how systems can go down. Or maybe you care about, detecting whether or not there's a chemical in a particular matter in the air. For all these things, you might want a Bayes net. They're a very powerful tool. It's just a general way of thinking about probability and what a language to have. So if you want to be working on this skill, creating a Bayes net, we have to be able to come up with a structure, but then we also have to define for every random variable its probability given its parents. You can express that in a few ways. You can express it mathematically, or you can express it through code. What a time to be alive. And then, of course, as we mentioned, the assumption in the Bayes net is that if you take the probability of every random variable given the values of its parents, if you multiply all those together, that's where the joint comes from. So it's a simplification of how to express the joint. Okay, that's where we left off. What we haven't really talked about is how do people in the real world design these? Like, if I gave you a data set, you could make a Bayesian network. But you'd maybe know the causality. And if you know the causality, you're done. Just draw your nodes and put the causality. But I want to give you a real world data set where people might want to design the Bayesian network. The real world data set I have for you guys is all these people in the UK saying what sort of music they want. So every row here is a person in the UK saying 1 to 5, do I like dance music, folk music, country music, classical music, musicals, pop, and so on. And you'd like to have a model of how all these random variables are interacting together. Making a joint table would be too hard. But if you could come up with a Bayesian network which says how these different random variables might be causing each other, you could express this entire complex system in O of n space. If you could design this, great, you have an expression from which we can solve probability questions. We'll start to be able to say things like, okay, you listen to a punk song, therefore I think you like punk, which will change my belief in all these things, and I'll have a better belief of whether or not you like reggae or opera. And you'd be able to do all these wonderful inference tasks if you could design it. Now maybe you just know how music works, and maybe you just sit down and be like, okay, people who like pop music also like, class music, like opera, dancey music. They maybe like punk music too. And like maybe you can just design this from scratch. But one of the cool ideas we touched on at the end of yesterday's classes, there are data-driven things that I do when I'm given a data set to try and inform my decisions. And one of them is I take every random variable and I see how much it covaries with other random variables. So if one random variable tends to, if for like a person, they tend to be more rocky, then how does that change my belief in whether or not they're into classical music or dance music or alternative folk music? It would be great if we had a statistic, and I do have a statistic that I calculate for every pair of random variables. That particular statistic that we talked about lightly, and I just want to finish the conversation on, is called covariance. And covariance measures for two random variables, like let's say x-axis is how much somebody likes heavy metal rock, and y-axis is how much somebody likes, let's say, punk. When people tend to deviate from the mean in a positive direction, so they're more likely to like heavy metal rock than the average person, they're also more likely to like punk than the average person. So these two random variables, when people deviate from the mean, they tend to deviate in the same direction. And we can measure that. We can quantify what we want as this. It's like the expectation of the product of the deviations of the means in both directions. And if you were to then rework the mathematics of what this is, you would get that it's equivalent statement to take the expectation of the product of the random variables minus the expectation of one times the expectation of the other. Something you could calculate from data. And this is a measure that people use to try and suss out are two random variables related. I want to talk about this a little bit because it's just a cool concept and something that you're going to need later on. So it's a cool concept buried in this idea of Bayesian networks. Can I just tell you a little bit about this number? So there is this number you can calculate for any two random variables. And when I see a high value of that number, I think those two random variables are very related. When I see a very high negative value, I think that those two random variables are related, but in a negative way. So if you see one random variable becoming high, you expect the other random variable to go low. But when I see a 0, it turns out there's a complicated analysis. I think that there's one of two things going on. Either they're not related, or the relationship is somehow not captured by this number. Can I give you an example of two very related random variables whose relationship is not captured by this measure of how much two random variables covary? Okay, here it is. There's not a beautiful picture to go with it, but it's a simple idea. Imagine I have a random variable that's -1, 0, or 1, equal probability. So a 1/3 chance of being each of those things. On its own, that's fine to think about. And I'm going to have a second random variable, and it's so related to the first random variable that if you tell me what x is, I will tell you what y is. If you chose x to be 0, then y is going to be 1. If you chose x to be anything other than 0, y is going to be 0. Are these two random variables related? Oh yeah, one is defined in terms of the other one's value. So if you tell me x, your belief in y will really change. In fact, you'll know what y is. They're not independent at all. But I just want to show you the limitation of this measurement. So x, it's a 1/3 chance of being -1, 1/3 chance of being 0, 1/3 chance of being 1. Y is going to be determined based on x, and it turns out because as long as x is 0, then y is 1, there's a 1/3 chance that y is 1 and a 2/3 chance that it's 0. What you have in front of you is the full joint probability table. If you were to calculate the covariance, you'd first get the expectation of x. Well, the expectation of x, you're going to take each of these numbers and weight it by its value. Good times, expectation review. Know how to do that by Tuesday. What if you wanted the expectation of y? What a reasonable thing to want. Well, y can take on two values, 0 and 1, and it takes on 0 with the probability 2/3 and takes on 1 with probably 1/3. So its expectation of 1/3. Not so bad. Now, no matter what value x is, or if x is 0, then y is something non-zero. But if x is non-zero, then y is 0. One of them will always be 0. So if you multiply x and y, no matter what value x was, that product will be 0. So in all cases, the product of x and y is 0. So the expectation of x and y is 0. Now, if you want to calculate this statistic we've been talking about, this measure of covariance, it would be 0 minus 0 times 1/3, which leaves you with 0. So covariance, it's supposed to be a number which captures how much these two variables covary. It's in the freaking name. And yet, even though these things are very deterministically related, covariance ends up being 0. What's gone wrong here? Covariance is one number to capture a very complicated concept. If you have very large values of covariance or very large negative values, that is meaningful. But covariances of 0 could mean one of two things. Either there's no relationship, or there is a relationship, but somehow the covariance is washing out. And there's a very fancy proof that shows that this is going to be 0 if there's somehow a very nonlinear relationship, but that's a little bit beyond the point of CS109. The point of CS109 is you need to know that there's this thing covariance between two random variables. I want you to think about it when you want to construct a Bayes net as a way to get information, and I want you to be able to interpret those values, and I want you to know that even though covariance is a signal of relationship, covariance of 0 could mean few things. It's not a proof that they're independent. Yes?
Well, the value of a covariant, if we calculate the covariance of two variables, will the result always be between 1 and -1?
It will not be. What a good question. So that's the first problem is this one. And the second problem that we're going to talk about in a second is that it's not bounded. Covariance could be a large or small number. So let me give you a concrete example of that. Here is weight and height for some people, and you could calculate the covariance, which says to what extent do these two random variables vary together. And you can get the covariance formula, and you can calculate each of the terms, and then you can get a covariance of 46. And you're like, does 46 mean anything? Is 46 large? It's smaller than like 2,000, but it's bigger than like 5. I don't know. Is this a meaningful number? And people thought about this for a while, and they thought, okay, even though covariance is semantically something we care about, people don't know how to interpret these numbers. So come along a very fancy person who came up with a very fancy idea. There is something called the Cauchy-Schwarz inequality, which the proof is beyond CS109, but the conclusion is this. If you calculate the covariance of any two random variables, it is always going to be less than the standard deviation of one random variable multiplied by the standard deviation of the other random variable. And it's also always going to be larger than the negative of that. It's not possible for them to be bigger than this product. Proving that's beyond class, but the result of that is a different number that you've heard about. You've heard about this thing called a correlation. And the correlation is just a normalized version of covariance. We take the covariance and we divide it by this number. Why this number? Because we know that the covariance will always be less than this number. Why is that nice? Correlation is a scaled version of covariance, which is always between -1 and 1, which is great. If you go back to this plot, I actually used correlation here instead of covariance because I wanted everything between -1 and 1 so that everything was on the same scale. So correlation is a scaled version of covariance, and covariance is your measure of how much two random variables relate to each other. Okay, and then since it's a Friday, I just have some like relaxing, chill, let's laugh at correlations. So one problem I've talked about for correlations is a correlation of 0 doesn't mean that two random variables are actually independent of each other. They could be very dependent, just their relationship isn't captured by this particular way of talking about them deviating from means together. But this is a little bit funny too. Sometimes things have high correlations, but they're not at all related. So if you go into data, people have mined for funny correlations. And here's two random variables that just happen to correlate, but we think there might not be a deeper reason. Rock music quality and US oil production. So apparently like the 1960s were like the golden age of rock music, and there was a whole bunch of US crude made between them. This ends at 2007. But we don't think that oil is causing rock music, and we don't think that rock music is causing oil. I'll ask you why there might be high correlations for these things. So think about that for a second. Two other things that have high correlation but maybe aren't that related. Per capita consumption of cheese and number of people who died by becoming tangled up in their bed sheets. Unrelated, but they tend to have a high correlation. Divorce rates and butter consumption. Butter consumption is down, so are divorce rates. Is it a coincidence? Perhaps, perhaps not. Does anyone know why these things that seem unrelated might have high correlations? Yeah, in the back.
There might be something else that's causing them.
There could be something else that's causing. That is possible. It turns out for these three, there's a different mechanism going on.
Excess of data.
Yes.
Like can find relationships.
Yeah, if I took a random number generator and a different random number generator and I generated a data set from them, they're probably going to be uncorrelated because they're all random. But if I repeated this process a billion times, two random number generators are going to produce a random set of data, and it'll just happen to be that they look correlated. If you look for enough pairs of random variables, even if they're all unrelated, eventually, just by chance, you'll find two that happen to be high in this correlation thing. So there's we are fishing through too many data sets to find correlations. Anyways, that's just a fun aside. But the real reason I brought it up is because when I look at a big data set and I don't know how to model, one of the pro tips that I would use is I calculate the correlation between every pair of random variable to try and figure out which ones are related to each other. So at this point in the plot, could you create a Bayesian network? Well, sure, there's a few options. For the structure, you could either guess at causality, or you could calculate correlations and again, try and artfully design a nice Bayesian network. You then need to give the probability of every child given its parents. We'll talk about that in a bit. But at this point, sure, you could create a Bayes net if you needed to. Question?
Mathematical way to determine the direction of causality.
Is there a way to determine the direction of causality? A little bit. Here's what's easy to do. You can disprove causality, or you can have a high probability that there's not causality. It turns out it's very hard from historical data to say there is causality. Maybe you've heard the thing like correlation does not imply causation. It's very hard to pull out causality. Though it turns out sophisticated mathematics can disprove different causal relationships. Yes?
Last class we talked about how the flu might cause you to be tired or might cause you to have a fever. How does it work where it's like the opposite, like something causes something not to happen? Like, does that work in a Bayesian?
Yeah, you would still use causality. So if I don't know, taking a vaccine will mean you're less likely to have flu, I would still call that causal, even though it's like a negative cause. It's still one is really influencing and creating the value of the other one. Good question. But the real point of today's lesson is, let's say you have a Bayesian network. I want you guys to now be able to solve any probability question you might want to ask about it. One option is algebra. So by algebra, I mean take this Bayesian network and you can just calculate using pencil and paper or maybe a piece of Python any probability question. We talked about this one where you compute the joint just by calculating the probability of things in order from parent to child. So probability of flu times probability of undergraduate times probability of fever given flu equals 0 times the probability that tired equals 1 given that undergrad equals 1 and flu equals 0. If you multiply all those things together, you can get the probability of the joint. It's like the Bayesian network is hiding probabilities of joints. It's a way of representing joint probabilities. But if you wanted to do a conditional probability, we talked about this last time. You could still do it using joint probabilities. I mean, using joint probabilities, you could know the probability of any particular combination to all random variables. And because of this, you could use the definition of conditional probability. This probability is equal to the probability of everything divided by the probability of the right-hand side. But that probability of the right-hand side, you can get through marginalization. You can take your joint, and you can think about the case of the right-hand side, these three, where flu equals 1, and the case of the right-hand side where flu equals 0. Add those two things together, you marginalize out flu, and you're just left with the probability of the right-hand side. So that works. It's one way to calculate. But what about this probability? So I have a little challenge for you guys. Chance for warming up, chance to meet the person next to you. How would you calculate this conditional probability? I've given you a Bayes net, which means basically I've given you a way to calculate the probability of a joint. Could you calculate this probability? And I encourage you to think, well, I've got the joint. if I write this in terms of conditional probability, could I use the fact that I've got a joint to calculate each of the things in my definition of conditional probability that I need? Can you go from a joint to a probability of an assignment to fewer random variables? Think about it, talk to the person next to you, and then we're going to come up with something altogether. Okay, let's talk together. Questions, concerns, what's confusing about this? I wrote the definition of conditional probability for the thing you're supposed to calculate, and I want to remind you that with a Bayesian network or any probabilistic model for many random variables, the first thing is to make sure you can calculate the probability of a joint, which is, if you're thinking about it as like a programmer, it's like I'm giving you a function. If you give me an assignment to all 4 random variables, I've got a function which will give you the probability of that joint assignment. What I don't have is a calculation for the probability of just 2 random variables. So I've got this, I want these things. Is there a way to go from one to the other? You could use law of total probability. Yes, it has another name. It is the law of total probability, but the law of total probability has another name often when we're talking about many random variables together. Does anyone remember what that other name is? Marginalization, law of total probability is the same thing. It's just law of total probability applied to joints. So if you use marginalization, it's a way to go from the fact that you've got a probability of many random variables to calculating a probability with fewer, where you just don't know if somebody's got fever or you don't know if they've got flu. So, again, if you want to know the probability of flu and fever, you want to think about all combinations of undergraduate and tired. So, one way of thinking about this, this is for the top bit. So this is the one where you just don't have fever. So for the top bit, it's like you're going to add in fever equals 1 with fever equals 2. And if you add those 2 probabilities together, you marginalize out fever, and you're just a probability of this and this and this. Fantastic. For the bottom, we need to marginalize out both flu and fever. And so it's like you loop over all possible combinations of flu and fever. And for each of them, you calculate the probability of those things you're marginalizing out with the probability of the things that you're holding constant. And then you can end up with just the probability of undergraduate and tired. Yes, you're left with just the probability of undergraduate equals 1 and tired equals 1. Marginalization allows you to go from knowing probability of many random variables to knowing the probability of fewer of them. Yes?
How do you determine what needs to be marginalized out, and how do you, what does it mean to marginalize something out?
Okay, so I want this. I want U and T. What I've got is U and T and the 2 F's. So I know I need to marginalize out the two F's. And to marginalize out, I just sum over assignments to the two F's. So I'm going to call X my assignment to flu and Y my assignment to fever. So you have to sum over the ones you don't want. Take the joint, sum over the ones you don't want, and you're good. If you did this, then you would end up with a probability that somebody has the flu given these two assignments. This is great, and you can definitely calculate this, but it does get a little bit complicated. You know, it can become really hard. If you had thousands of random variables and you only observed 2, you're going to have to marginalize out every unobserved random variable. And think about WebMD. You could have pain in your toes. You could have a headache. You could have a stomach ache. Maybe you just feel a little bit tired today or funny. Like there's thousands of random variables, and we have to marginalize them all out. Hey, sorry, guys. Okay, and so if you have too many random variables, you have to marginalize them all out. This calculation is going to become really, really expensive. Darn it. We were doing so well. We want to be able to do inference, and we want to be able to do it in a scalable way. But right now, even though we've got a mathematical way of doing inference, it's not going to help us as computer scientists. We need to think of another way. And the beauty of the way I'm going to teach you, I will teach you a more general way that is very powerful, but it also covers so many intuitions about probability. So if you can follow along, not only are you going to learn an amazing randomized algorithm that will teach you how to do inference for any Bayesian network, or any probabilistic model for that matter, it's also going to just like teach us some good, hearty probability along the way. The very simple idea is we're going to have this thing called rejection sampling. Step 0, you have to define a Bayesian network, and you have to define it in code. To define a Bayesian network in code, you basically need to write all these probabilities, and you have to write a function which can generate a sample of the joint, or calculate the probability of a joint. The steps are going to be, maybe you're going to get an observation from the user. So the user is going to tell you, I observe undergraduate and I observe that somebody's tired. There's no algorithm here. This is just the user telling you the puzzle you have to solve. And now we're going to try and figure out the probability of the flu given their observation. And there's a 2-step process. And it's so straightforward. You guys could have invented rejection sampling yourself. The straightforward way is, can you generate me a whole billions and billions of fake samples from your joint? And we're going to put that into a big data set. So give me 1 billion fake examples from your joint. And then to calculate any probability, I'm just going to resort to counting. So it's got like a little bit from every part of class. You've got a bit from like the probabilistic models part of class. You've got a bit from like the foundation part of class, and a little bit of counting for the beginning of class. And through all this, you're going to be able to do the inference task for any probabilistic model. It's going to be that straightforward. Are you guys ready for it? You should have 2 questions. Your first question should be, how do I sample a ton? And the second question should be, how do I do counting if I've got samples to answer any probability question? Shall we jump into the first one? How do we sample a ton? It's this easy. If you want to sample a ton, you loop many times and make 1 sample and add that to your list. You're like, oh, Chris, that's a very satisfying answer. Says nobody. Why is this not a satisfying answer? It's like, okay, sampling a ton obviously requires you to be able to create samples. What I really want to understand is, how do you create a sample? Creating a sample means I'm just going to generate 1 fake person. And this fake person, we're going to observe everything about them. We'll know if they have the flu. We'll know if they're undergrads. We're going to know if they have fever. And we'll know if they're tired. In fact, we did this a little bit on Wednesday's class. I showed you a function like this. And this function made me a fake person where you observe everything about them. You observe if they have the flu, an undergraduate, fever, or tired. Not that they have an undergraduate, whether they are an undergraduate. If you run this, it gives you 1 person. And it turns out that person's probability of having this particular assignment comes straight from the joint. If you run this 10 times, you'll get 10 people where you'll observe everything. If you run this 100,000 times, you'll get a whole 100,000 fake people. If you look at any particular assignment, like they have a flu, they are an undergraduate, they have a fever, and they are tired, like 1s to everything, the probability of seeing 1, 1, 1, 1 will be the true probability according to the Bayesian network. If you generate 100,000, let's say the probability of getting a 1, 1, 1, 1 is truly 10%. If you generate 100,000 of these, you would expect to see 10,000 people with a 1, 1, 1, 1. Sampling is such a nice intuitive idea. It's sometimes weird to think about, but do you guys know in problem set 2, where you guys had to write a function which would sample from a Poisson? Like you'd run the Poisson function, you'd pass in a lambda, and it'd give you back a number. That's a sample. And then you wrote the exponential function, and you would run it, and it would give you back a number every time you ran it. That's a sample. This is just a joint sample. Instead of giving you one number, it's giving you a number for every random variable. OK, this is half of the algorithm. So maybe you have questions. It would be great if you had questions. I would love to talk about it. Yes?
How do we guarantee that that probability in the end is sampled from the joint?
I guarantee you that it's sampled from your Bayesian network. And if your Bayesian network is any good, this will be a really good representation of the real world. If your Bayesian network is totally made up and completely useless, then so will these samples be. So if your Bayesian network's good, these samples will be good. But they perfectly represent the network. Yeah, question?
How is burn implemented?
Oh, burn. I get a probability uniformly between 0 and 1. And so maybe when you pull a number between 0 and 1, you get like a 0.892. And if that number is less than the parameter, then I return back a 1. Otherwise, I return back a 0. Yeah, lots of good ways to implement it. Yeah, question?
How wrong would your sampling be if you had the arrows in your Bayesian network flipped? Like if you had the children as the causal parents?
Good question. You know, it's hard to quantify. But what I'd tell you this is, if I were to try this out, I might do something like have a few Bayesian networks, and maybe I'd have some people for whom I know whether or not they had the fever, and I would try seeing which Bayesian network is leading to the most accurate predictions. But otherwise, if you flip the arrows, you'd be wrong. It'd be so hard to come up with the probabilities. Like the probability of being an undergraduate given you have a fever seems like a harder probability to come up with. But even if you did it, and if you came up with reasonable probabilities, you would still get a reasonable answer. Have you guys heard this saying, all models are wrong, but some models are useful? Turns out the more realistic your model looks, the better your answers will be. But even if you're a little bit wrong, you'll probably get pretty good answers.
I think I'm just so confused. Like back to the covariance thing, like since we can't determine causation from covariance, how does it actually help us create our network?
I mean, it's an art form. Creating a network is an art form. It turns out there is this algorithm called structure learning, which you'll learn about in CS109, where you can just like learn the whole thing purely from data, and you try and do things like learn different causal patterns which can't be there. There are algorithms for that, but I'd say most people making Bayesian networks, it's art and love and dedication and data. So they'll look at the correlations, they'll come up with their understanding of how the world works, they will artfully create a Bayesian network, and then they'll probably test it. Maybe they make a few Bayesian networks and they'll test them, see which ones come up with the best predictions. It's a good question, and the real answer is art and craft. But you need it, because if you don't do it, you're stuck in something where you can't even compute. Yes?
Summarize, you basically randomly generate people from your probability model, and then you see if any of those people can exist.
Well, yeah, now you're getting into my second step. All I've done so far is make a bunch of fake people. But the important thing about the fake people is that for every fake person, I can see all of their variables.
How many fake people?
Hey, how big is your computer? I'd say 100,000 will just take you a second. But if it was like life or death, then maybe you want to do like 200,000. I'm kidding, the choice is yours. There is a formal way to think about how many you'd need, and we'll talk about that later. But basically, just recall, if you're making a fake person, start with choosing the values of the parents of the network, and then you choose the children. Like fever is dependent on whether or not you had a flu. So you want to choose flu first. And tired is dependent on whether you're undergraduate and flu, so you want to make sure you choose tired after you choose those two random variables. And after this, you've sampled. I have explained to you half of this beautiful randomized algorithm. Do you guys want to hear the other half? The other half is called rejecting. And that's why it gets its name, rejection sampling. But just to be clear, after I call this part of the function, I'll get a whole bunch of fake people. And in this fake data set, this was flu, this was undergraduate, this was fever, and this was tired. Everyone's tired. The second half is simply rejecting and counting. The simple idea is, if you want to figure out, say, the probability of somebody having fever given they're an undergraduate and tired, you're going to go through all of your 100,000 fake people, and you're going to throw away every data point that's not consistent with these observations. Recall, when we taught you conditioning, what were the semantics of conditioning? You enter the world where these two things are true. With your data set, you can enter the world where undergraduate is true and tired is true. And you can do that by only looking at the samples that are consistent with those two things. So you take your 100,000, you throw out all the grad students, you throw out all the professors, you throw out all the babies, but I just mean from your data set. And you throw out everyone who's not tired, and you're just left all the undergraduates who are tired. That's the first step. So you can call it rejecting, or you can call it keeping the ones that are consistent. So I'm going to loop over every sample, and I'm only going to keep the ones that are consistent with my observation. So for every sample, I'll see, are you an undergraduate and are you tired? And if so, I'm just going to keep that sample. After this step, kept samples will be strictly smaller than 100,000. Well, it'll be 100,000 or smaller. Now you've got a small subset of data of all the people who are consistent with undergraduate and tired, and your simple next step is, from that smaller data set, count how many people have the fever. So if you have, let's say, 30,000 people in your fake data set who are undergraduates and tired, you're just going to figure out the ratio of how many of those have fevers. So if 10,000 of those people have fevers, then the probability of fever equaling 1, given undergraduate equals 1, and tired equals 1, is just going to be approximately equal to this ratio. And I'm done. And you've calculated conditional probability. And the beautiful thing about this is you can change your observation. You could possibly even keep the 100,000 fake people, and you can calculate any conditional probability you want for any network. Cool or what? Do you guys want to see this thing in action? Okay, let's do this. No more slides. Take me to the code. So here I have the same program. It's just now I use underscores instead of camel case. I fought that hard. When I switched to Python, I still did camel case. Everyone else did underscores, snake case. I fought it hard, but I've finally come around, and I've drunk the Kool-Aid, and I'm one of the kids who does underscores now. Not important. What is important is rejection sampling is a cool algorithm.
How is this related to the rejection sampling of simulating a continuous PDF from a different PDF?
Wait. We'll talk about continuous in a hot second. Good question, though. I want to first just show you guys this thing in action. So I'm going to run it. It's called joint sample. You know, when I first taught this, I didn't want to call it rejection sample. Doesn't that sound so mean? I don't like to reject people. That's not what I'm about. I'm about solving inference tasks, but I don't want to do any rejection. So I call it joint sampling, but then I realized that's not what people in literature call it. So now you know. Here's the simple thing. I get an observation from the user, and right now I just hard-coded that. So I said, my observation is that somebody has a fever, and they're an undergraduate. But I don't know if they're tired, and I don't know if they're flu. If I want to say I observe that they aren't tired, then I would make this false. But if I put none, it just means I don't observe whether or not they're tired. Do you guys want to give me an observation? We're trying to predict if somebody has the flu. So we want to keep that one none. Okay, this person, do they have a fever? Let's just yell it, and I'll just go with what the math says. Do they have a fever?
Yes.
Oh, poor them. Okay, are they an undergraduate?
No. No.
Oh. Are they tired?
Yes.
Wow, that's incredibly consistent. Okay, we have somebody who is not an undergraduate, but they are tired, and we want to know if they have a fever. So we're just going to sample a ton. We're going to throw out every sample that's not consistent with our observation, and we'll figure out the probability that they have a flu. In this case, it says these people, this person, 95% chance definitely has a flu according to your Bayesian network. Now, you could try a different one. I just want to give us one other example. I'm going to show us having no observation for tired. In fact, actually, should we do this one? Should we do undergraduate equals 1 and tired equals 1, but you don't know if they have a fever? Okay, undergraduate equals 1, true. We don't know if they have a fever, but we know that they are tired. So here, none means you don't know, and true means you know, and it's a 1. Okay, undergraduates who are tired, how many of them have the flu? So you're just like, I'm tired. You probably don't have the flu. Now, if you tell me you don't have a fever, so now you're saying, I'm tired and I know I don't have a fever, I kind of expect that probability to go down because now you just told me more information. Yeah, you tell me you definitely don't have a fever, I'm like, yeah, it's probably just tired. Could be the flu. 1% chance it's the flu, but you're probably just tired. Yes?
How is this different from what we were doing like on the first P set when we were trying to figure out the genes, if they were causing the traits or not? I feel like it was the same process.
Yeah, when you were trying to figure out for the genes if they were causing the trait, what you guys were looking for were independencies. You know what you guys were secretly doing? You were secretly trying to find the structure of the Bayesian network. You weren't necessarily calculating the conditional probabilities that you would need to pull out a sample. Like, it would be hard for you guys to sample one row of that data set. But once you have the data set, then yeah, the conditional probabilities were just counting. Like the second step of this, you use the exact same thing for the BAT data set. So first step of BAT was just really about creating a Bayes net, and the second step was about doing the second half of rejection sampling. You already had a real data set, you didn't have to simulate it. Yes?
Do these like different traits have to be independent? Like, could you ever integrate with like conditional probabilities?
Oh, these things are very much not independent. There's a whole Bayesian network that is explaining their relationship. So if you're undergraduate, that very much changes our belief that you're tired. If you have a flu, that very much changes our belief that you're fired. So, you've got a fever. So you have a lot of things that are very much related.
So how does it like making the joint table work if it's like if they have different conditional probabilities? Like, that affects.
The conditional probabilities are encoded here. Let me show you where they're encoded. There is a part where you have to sample. Where's my sample? There's my sample. Aw, high sample. So there's your part of your code where you sample. And this is where all the probabilities lie. I'm saying the chance that you have a flu and the chance you have undergraduate. The chance that you have a fever given you have a flu. The chance that you have a fever given you don't have a flu. The chance that you're tired given this particular setting of probabilities. Like, I've defined all these conditional probabilities. I've put them into Python, and I put them in Python in a way that I can create one sample. These conditional probabilities are true for everyone. The model is universal. But if you have a particular human being, they might show up and you might want to do a query based on some traits. The model is universal. The query is for particular individuals. But the conditional probabilities in the model, they'll be for everybody. Good question. Yes?
I just want to summarize to make sure I know what's happening in this code. So
Yeah.
what you're saying is that we're going to take out all the samples that don't meet the initial conditions that we set.
That's the second part. This is the first part, which is generating a ton. Do you guys want to see the rejection part?
Yes.
Okay, here.
So we take out, for example, everything that is not undergrad equals 1 and tired equals 1.
Perfect.
And from that, that's the denominator. And the top is from those samples. We go through and see what samples have the flu equals 1 and then just put that over it.
Yeah, so I just go through all the samples and I count how many people have the flu. And then I just return, well, I didn't need to do float, but so it goes. How many people had the flu divided by how many samples I kept. You got it exactly right. Okay, full rejection sampling. I imagine there's probably questions at this point though, so I really appreciate them. But it really comes down to get the query from the user. This algorithm will handle any query for this model. Then we're going to sample a ton, and then we're going to calculate our conditional probability just by rejecting and counting. And then you can solve any probability query you have for this particular model. And the real challenge wasn't the rejection part. The real challenge is only, can you write the sample? And so if you have a Bayesian network, and you can write this function which does the sample from the Bayesian network, then you can solve any inference task. So I'm going to put a little check mark here. I do owe you an explanation for continuous random variables, but we'll get to that in a second.
Do you have to make more samples if you know you're going to reject more?
Yes. If you know you're going to have to reject more, you would need more samples, and that's why continuous becomes so interesting. Okay. So at this point, you know, if I gave you a thing like WebMD, if you want to make a Bayesian, tell me how you think the world's organized, and then you need to get your conditional probabilities. You can either talk to an expert or use a data set for those. Then once you have a Bayesian network, we can use rejection sampling and answer any probability question we've got. Okay, so here's the claim behind rejection sampling. It's not that crazy. The claim behind rejection sampling is that this conditional probability is about equal to how many samples are consistent with the observation and what proportion of those are consistent with the observation and also have flu equals 1. And this really harks back to the original definition of probabilities, which is saying that the probability of our event of somebody having a flu is the ratio of number of times that happens. This is in the universe of what we observed. So in the universe of what we observed, what fraction of people have the flu? So it's like counting number of people with flu divided by the number of people in this particular universe. So the universe of people who are undergraduates and are tired. So the theory behind it's rather straightforward. And this is why rejection sampling works. What does it require you to understand? You need to know what a Bayesian network is. You need to know what it means to sample from a Bayesian network to get a whole joint sample. And then you need to know the simple idea of counting. And then you can answer your inference questions. Yes, Mia.
Would we be required to sort of introduce those rejection algorithms?
You know, I can use Bayesian networks to create interesting joint probability questions. So there's, you know, things from your last section where you guys talked about joint distributions, and a Bayesian network is just a really elegant way for expressing a joint. Would I make you guys do rejection sampling on the midterm? Maybe not, because, you know, the code for rejection sampling, it's always the same. Like, this part of the code is always the same. The only part of the code which is different, if you were to do it differently, is to write this code where you pull a single sample. Would I make you write a code that could pull a single sample? I'm definitely going to ask it for you in the next problem set. I think on the midterm, I probably wouldn't make you do this. I would possibly, though, you know, I think this is fair game. This idea that you can count to calculate a conditional probability. So if you have a data set like the bats that we talked about earlier, you could get probabilities by counting from subsets. That's very much fair game. Good question. Okay, now, if you can sample enough from the joint distribution, you can answer any probability question. Wow, what a fun time. But there is a problem with rejection sampling. And the problem with rejection sampling is if you condition off something incredibly rare, so if you condition off something that hardly ever happens, and if in your 100,000 fake samples you just didn't see the thing you condition off of, you'll reject everything. So imagine you're conditioning off like a very rare occurrence, like somebody has a fever, but you know, maybe they don't have a flu. Like, this almost never happens. If you condition off that, you take your 100,000 samples, you look through all of them that has that particular assignment, and maybe you throw away everything. And if you throw away everything, you've got a problem, right? Because the definition of probability here was supposed to be, you know, the limit as n goes to infinity. And if you throw away everything, you're left with like 0, 1, 2, or 3 samples. This is getting pretty far away from the definition of probability that we were using. So the problem with rejection sampling is if you reject everything, kind of like the problem with life. So let's think about this a little bit, and I can give you a particular version of this which really breaks rejection sampling. And that's if I took my Bayesian network and I allowed for a continuous random variable. Fever is not something that's a 1 or a 0. It's a continuous number. You say, I have a fever of 92. Wait, I have a fever of 102. You don't say, I just have a fever. So what if we wanted to take a Bayesian network and we want to allow one random variable to be continuous? We have seen Bayesian networks with continuous random variables. Like, for example, the elephant one, we would have weight as a continuous random variable. Or in the gaze, how much the child's view moved, that was a continuous random variable. So we have seen it before. And the way we saw it were things like this. If somebody has the flu, that's definitely wrong. If somebody does have the flu, then the distribution of their temperature is going to be a normal with a higher mean. And it turns out there's quite a bit more variance. If somebody doesn't have the flu, then the distribution of their temperature is the average temperature of a human, but there's also variance to the average temperature of a human. Some people present with like 99 degrees even when they're healthy. But when people have a fever, it could be anything from like 98 to 102. There's a whole bunch of variance. So this is a more precise way of expressing fever. Does that make sense? Okay, so at this point, we've got a Bayesian network. Could we still write a sampling algorithm? Because that was the first thing we need to do. As I said, the most complicated thing we'd have to do is a sampling algorithm. Could you sample flu for a new person? Yeah, that's good. Can you sample undergrad? Yeah, it's just going to be that burn 0.8. Could you sample tired? Well, if they've got the flu, if they're undergraduate, and we're just using the same algorithm, so yeah, we could. Could you sample fever? If you're making a joint sample. Talk to the person next to you. How would you sample fever? See if you can figure it out, and then we'll just check or not check if you can sample fever. How would you do it? How would you write this in Python? I don't know what you guys came up with. But it turns out the answer is yes, you can sample. Here's what happens is you go back to your sample, you have to choose flu first. Because flu is 1, we're going to be sampling from different normal distributions. If flu is 1, we're going to be sampling fever from a normal distribution with that higher mean. If flu is 0, we're going to sample from a normal distribution with that lower mean. Now norm, that's not a function. Here's how you sample from a normal. SciPy has a stats library, and you can see stats.norm.rvs. You just pass the mean and standard deviation, and it will give you a random sample from that normal distribution. So can we sample? Absolutely. The problem isn't that we can't create joint samples. And if we go to our code, I'm going to now create an observation. My observation is somebody is an undergraduate and they are tired, and we observe a fever of 101. And I'm just going to use the exact same rejection sampling. Now we've got those normal distributions to sample for fever. Let's do this. Python 3 joint sample continuous. Here comes our fake people. And look, they've all got temperatures. How cute is that? It's so much more exciting. Ooh, there goes their numbers. That's not right. I might have played around with this, and I must have fixed something. Because that probability was supposed to give us the surprising result of a null. Okay, let's see my check observation match. I'm not doing anything really fancy here, am I? Sorry. Print observation. Oh, wait, I know what I did here. So cute. Oh my God, so cute. So cute of me. No. Okay. Back to my demo that was supposed to fail, but somehow didn't fail. Now it really failed. Probability is not defined. Terminal. New terminal. I feel like people go to watch race cars because there's a chance that they'll crash. Okay, here comes my fake people. And from these fake people, we're going to reject everything that doesn't match our sample. Oh no, it broke. And our sample had, this is the thing we were going to condition off. So we rejected everything that didn't match this. And we looked for exact matches. And you're like, wait, something definitely matched that. And you go over and you're like, And you're like, that one matches, almost. And you're like, nope, not exactly. You're like, that one doesn't match. And you get to this one, you're like, that matches, right? No. You condition off an exact match. That is the proper probabilistic thing to do. You went through all your samples and you looked for 101.0. We've talked about this. For a continuous random variable, what's the chance that it gives you exactly 101.0? 0. That's never happening. Sad times. And so like sad times expressed in computer science is here. Aww. Division by 0. When I went to count, I had rejected everything, and I was just left alone without any samples, crying in my bedroom. Division by 0. And then, unfortunately, I had accidentally showed you the solution, or a solution. So a solution was, what if every time you generate somebody with a fever, you round it? So, does anyone remember the math, or the function for rounding? There it is. There it is. So, there's definitely a nice function for rounding, but Python has a round, and so you can just take any fever, and if you round it now when we create our samples, once they get rounded, you have a non-zero chance of people actually matching 101.0. Do many of these match 101.0? No, you don't see a lot of people, but you do see enough that you can calculate a probability. If you don't see many 101.0s, if that is a very rare event, how can it still be the case that the probability of fever is very high? The thing I condition off is rare, but the probability of fever was very large. Sorry, the probability of flu was very large. Because the thing I condition off is rare doesn't tell you about the probability of flu. What that tells you is I'm going to be rejecting a lot of my samples. So maybe of 100,000 fake people, only 100 of them had that particular fever temperature. But when we looked at those 100 people who had that particular fever temperature, a whole bunch of them actually had the flu. So, going back to the theory, well, maybe I should answer questions there.
Can you just clarify what you changed?
I made it round. So what I changed here is, when I generate my samples, before I would generate a continuous number to full precision, and now I just generate one to like 1 decimal point.
You've done the same thing by creating a small range.
Yeah, you could have said fever is low, medium, high. You could have said your fever is 100 or 90 to 95, 95 to 100, 100 to 100. Any way you discretize would work. And this is a way of discretizing. I'm just discretizing to 1 decimal point. So discretization is helping us once again. Yeah.
Could you just explain how you generated the random fever numbers?
Oh yeah. So I used Let's check this line out. So I'm just going to pull up Python. So terminal, Python, Pyron, whatever, from SciPy import stats. You want a random normal? But what normal? Give me a mean. 5. Ooh, good choice. Standard deviation. No, that's too big. No, I'm just joking, that's fine. Okay, I'm going to call this function, and it gives you 1 sample. So if I call it again, you get a different sample. It's not always the same number, and the distribution from which this comes is the probability density function. But it's not uniform. It's random from this particular normal. It's from the PDF of the normal. Yes? Oh, random variables, I think, or random values. And I think there might be a parameter where you can be like 10, and it might give you back 10 of these. Yeah. The S is for multiple, and because this function allows you to get multiple. How optimized is my code? And you're like, not at all. I could definitely optimize this, but the point is the learning, not how fast you could run this. Okay. Wait, I want to talk more about this. So if you guys have questions, this is very fun. So this is the thing we're trying to learn how to do, any inference task for any Bayesian network. And rejection sampling is such a good idea. It requires you to know how to do two things. You need to know how to sample, and then you just need to write rejection sampling. It fails if you're doing a query where the condition thing is so rare you throw out all your samples. And so we used a trick here to solve that problem. Questions? Comments? Concerns? Yeah.
Decide to what precision you discretize your work.
That's a good question. I think I made 100,000 samples, so that discretization gave me enough samples for each reasonable thing. But if I wanted to make 1 billion samples, I could probably get away with a finer discretization. So it's dependent on how many samples you have. It really comes down to what's the probability of your observation. And if that probability gets too low, it fails, or you need more samples. Yes?
Is there a way that we can do this without discretizing via some other chain?
Yes, there is. Next question. No, I'm just joking. I'll explain to you how in just a second.
I don't know if this is like outside the scope of the problem, but how exactly does the function that creates the normal distribution people work?
Oh, how does that work? Ask me after class, but I think I talked about it earlier. Basically, there's this thing called a CDF. It's a beautiful thing. And if you take the CDF of the normal you're sampling from, it turns out you choose a random value between 0 and 1, and you inverse transform onto that CDF, and you return back. This goes back to the user. So you start here, choose your y of the CDF, and figure out which x would lead to that y, give that to the user, and it gives you a proper sample. It's a beautiful thing. Okay. I'm not going to teach you this, but I'm going to teach you that it exists. There is this thing called Markov chain Monte Carlo. It is a cool algorithm if you want to go beyond rejection sampling. Rejection sampling works for so many cases, especially if you're just a little bit thoughtful about your discretizations. But I did want you to know that there are other things out there. And Markov chain Monte Carlo does the same thing as rejection sampling, but look at my samples. Notice anything funny? You're like, ha, 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 everyone has a fever. That's not funny, Chris. They've got a fever. That's scary. The interesting thing about this is even though I'm pulling samples, every single sample that I pull from has exactly the query in it. So it's like, set the query to be 101, and then choose the other random variables to be correct, given that the query is that number. And then you don't have to reject anything. How would you pull a sample like this is beyond CS109. It's super cool. You can go check it out. But it's the next algorithm if you were to learn beyond rejection sampling. Rejection sampling gets you so far, but there are other ones. There's MCMC. There's actually even a package written by Noah Goodman called Pyro so that you can just write this in code, and then the code will choose which algorithm it should use to do inference. A beautiful thing. And then we even wrote one in our lab for idea to text. And I'd love to tell you just a little bit about this. Do you guys want to hear about something cool? Yeah. Yay. OK, so I'm going to motivate this by a problem that doesn't feel like WebMD at all. The problem that I'm going to motivate this cool algorithm for is how can we figure out what mistakes students have made? So imagine a student's trying to write code to draw this thing. And if you think about it, it's like, that's pretty annoying code to write. You have to have like nested for loops. There's a whole bunch of things changing. It's very mind-blowing for a new student. And they're going to write it using a block-based language. Their solutions will probably be about 10 lines or less. But you need to then be able to say, what is the feedback I should give you? Your inference task is feedback given code. Those are hard random variables to think about, aren't they? And long story short, we wanted to use rejection sampling, something like it. So what did that mean we needed to be able to write? We needed to write a Python function called sample. And when you write this Python function called sample, it's going to make a fake student with all of their misconceptions and all of their code. And if we could write this sampling algorithm, then we could sample a ton, and then we can look out of all the sampled fake students, have we ever get all the students who have exactly this code? And we could look at all the students who had exactly this code, and we could say, okay, what misconceptions did they have? What's the distribution of people who didn't understand for loops here? What's the distribution of people who didn't understand if statements? So all we had to do was write a sampling function. And we were inspired by this picture. You're like, what is going on in this picture? In 2015, somebody wrote one of the more influential papers in our field, and all that they really had to do in this paper was write a function that was called sample, but instead of just sampling a regular random variable, it was sampling hand-drawn digits. So imagine you have somebody trying to write this digit, and there's all these other characters, and you might be trying to figure out what's the probability that what they've drawn is this character as opposed to this character. Well, what they had is they had a sampling algorithm. They wrote a generator. Boy, they should have used Python. In their paper, they wrote this crazy insanity, which is basically a mask around Python, where they would sample curves, sample connections of those curves, sample how people put those components together, and then from those, they could just write a forward generative process and end up with pictures of hand-drawn characters. And I said, if they can sample hand-drawn characters, we can sample code. They sampled a lot of hand-drawn characters, and they got very good results. They beat all the neural networks at the time. And so the idea was, can you do this for code? And so we just thought, okay, we're going to write sample. And when we write sample, we're just going to try and generatively think through a student's decision process. Okay, they decide to work on this problem. That's where they went wrong. Okay, and then we would set all their misconceptions, and then based on their misconceptions, we'd start to generate the code probabilistically, and we would sample from the joint as much as possible. It's like we made the Bayesian network, but for code. And we wrote a particular library that would allow us to write the Bayesian network for code, and it worked really, really, really well. And to the point where you could write this Bayesian network. Teachers don't know the generative process. Does anyone know the Bayesian network for how a student thinks? No. There wasn't a place I could go research and look up what is the Bayesian network. We did have to invent it based on just what we thought students would do. But generative is not so hard. If you're thinking generatively, it's like making the WebMD model. It's not that hard. You can be like, okay, I think flu causes fever. That's not insane. And similarly, you can be like, if people have this misconception, I've seen them write this piece of code. It wasn't insane for us to write this, and it turned out to be very, very useful. And not just for code. We used it on code. We used it on short answers. And by we, I mean some wonderful scientists, which also included our own head TA. Actually, the first time I met Will, you were like a freshman, and you came and you're like, I want to do some research. I'm like, no. Sorry, I'm just joking. But you're like, hey, can I have a challenge for winter break? And I said, well, we're thinking a lot about these sampling things. Could you sample, I think it was graphics. I gave you a graphics thing. I said, people who are in 106A, they do a pyramid assignment. Can you sample people drawing pyramids? And you sampled a ton, Will. And it was part of this wonderful research project that seemed to work very well. So we wrote the decision-making Bayesian network, and then we would sample a ton. We would get a bunch of fake students with fake code, and then we would do inference. We could have used rejection sampling. That would have worked pretty well. I do want to be honest in that we also used a little bit of a neural network to make our rejection sampling a little bit more efficient. But rejection sampling would have been fine for inference. Because we could, we used a slightly different one. Now, before I let you go, I just want to make this a little bit more relevant. You guys should be asking yourselves this question. Here's one of the weirdest things you could ask yourself while studying for a midterm. You look at a problem and you're like, what's the probability that this is a binomial distribution problem? Right? Isn't that what you're kind of doing? And in fact, if you want to really solve that, you know what you should do? You should write a Bayesian network. You should think, what's the generative process through which Chris creates binomial distribution problems? And if you could write that Bayesian network, you would know everything about how to solve any CS109 binomial distribution problem, right? Wouldn't that be cool? So I went ahead and did that for you guys. I wrote a generative model, and when you run it, I think currently it just creates like 100 random binomial distribution problems. And sorry, they're written all in HTML with latex in them. But it'll say something like, a ball hit a series of 30 pins where it can bounce either to the left or the right. The probability of a right on each pin is 1/3. What is the probability that the number of rights is 28? Did somebody just write the answer? Does it say the answer? Oh, there is the answer. Oh, there it is. It's very, very low. But anyways, I sampled that. I just had a distribution for it, and potentially using some rejection sampling or something like MCMC or something more complicated, you could put this as your query, and you can say, what is the probability that this is binomial given the query? Or you could even say, what's the probability of the answer? You can even say, what's the answer given the query? Anyways. But that is an interesting thing. A funny way to talk about studying for a midterm is to try and write your own. That's maybe one takeaway. I can't write that many problems. I'm an old man. I've written many midterms. I'm running out of creativity. And there's only so many ways you can ask about binomials and Poissons and all those things. I probably have a generative process in my mind. And if you tried to write your own midterm, you would have to generate. You would have to get into the generative process. And maybe by thinking about that, you would get really good at the inference task. Because one of the stories of Bayesian networks is the ability to generate is an important precursor to the ability to infer. Okay, I'll just tell you what we haven't talked about. As I mentioned, there is a field of study where you can learn the errors from data. That's called structured learning. We haven't talked about this. And we haven't particularly talked about how you could get these probabilities. Basically, I've told you to make them up so far. But it turns out that there are data-driven ways you could do this. If I gave you some historical data, you could infer these probabilities pretty well. I hope you guys have a fantastic weekend. Study for the midterm. We'll see you guys. There's no class on Monday. See you guys on Tuesday or Wednesday. Have a fantastic weekend. I'll be thinking about you guys a lot. Come to the review session that starts in 40 minutes.